Good day and Merry Christmas to everyone. This is Jing Poh from Xiamen University, Malaysia. Today, I am going to give a presentation on the topic Lipschitz Continuous Function. In this presentation, I will start by introducing continuous function and Lipschitz function, stating a proof about the relationship between continuous function and Lipschitz function, giving a rigorous proof and some example to have a better understanding. If you like my video, please do not hesitate to like, share, and give a comment under this video. Let's move to our background of the study. Firstly, continuity was introduced by Cauchy in 1821 in his famous textbook called the Analyzer. In the textbook, he mentioned that a function f is continuous in a range if there is an infinitesimal alpha such that fx plus alpha minus fx is also infinitesimal for all x in the range. Now, the definition of continuity is more rigorous as shown in the slide. We let D be a subset of real number and let x0 be a point in D. A function f from the set to real number is continuous at x0 if, for every epsilon bigger than 0, there is a delta bigger than 0 such that if the point x is in the domain D and the absolute of x minus x0 is smaller than delta, then the absolute of fx minus fx0 is smaller than epsilon. To have better understanding, the mathematical expression of the definition of continuous function is shown in the slide. Next, Lipschitz function was introduced by Rudolf Lipschitz in 1864. He found the condition in his study of the convergence of the foreign series of a periodic function. And I will introduce about the definition of Lipschitz function. Again, we let D be a subset of real number. A function f from the set of real number is a Lipschitz function if there is a constant c such that the absolute of fx1 minus fx2 is smaller or equal to the constant c times the absolute of x1 minus x2 for all x1, x2 in the domain D. And we say that the constant c is the Lipschitz constant of the function. This is a simple illustration of Lipschitz function. In the figure, we can see that two straight lines with the same absolute gradient, that is, if L1 have a gradient A, L2 will have the gradient minus A. These two lines are placed so that the intersection is on a point of the function f. Then, we can see that the whole function is in the shaded area. Next, we want the function to be always in the shaded area when we put the intersection in any point of the function, as shown in the slide. If we can find such two straight lines, we say that the function is a Lipschitz function. Next, I will give a relationship between continuous function and Lipschitz function by using a theorem. As shown in the slide, a function from the set D, where D is a subset of real number, to real number is a continuous function if it is a Lipschitz function. And I'm going to prove it rigorously. Firstly, we need to do some sketching to have better understanding. Our goal is to let the absolute of fx1 minus fx2 be smaller than epsilon, and we have the condition. The absolute of fx1 minus fx2 is smaller or equal to the constant c times the absolute of x1 minus x2. Thus, we want c times absolute of x1 minus x2 to be smaller than epsilon. That is, the absolute of x1 minus x2 to be smaller than epsilon divided by c. Therefore, it is reasonable to choose delta to be epsilon divided by c. Now, we start to prove our theorem. We suppose f is a Lipschitz function. By definition, there is a constancy such that the absolute of fx1 minus fx2 is smaller or equal to the constant c times the absolute of x1 minus x2 for all x1, x2 in the domain D. Then we let epsilon to be bigger than 0 and choose delta equal to epsilon divided by c, which is also bigger than 0. Next, assume that the epsilon of x1 minus x2 is smaller than delta. Then we can find that the absolute of fx1 minus fx2 is smaller than epsilon. This implies the continuity, which is for any epsilon bigger than 0, there is a delta bigger than 0 such that if the absolute of x1 minus x2 is smaller than delta, then the absolute of fx1 minus fx2 is smaller than epsilon. Now, let's look at some examples to have better understanding. Let f be the function defined by f equal to ax plus b. We need to show that f is continuous by showing it is a Lipschitz function. Let's look at the solution. We know that the absolute of fx1 minus fx2 is equal to the absolute of a times the absolute of x1 minus x2, which is also true for the smaller or equal case. This implies that f is a Lipschitz function with Lipschitz constant absolute a. So by the theorem that we have said and proved before, f is a continuous function. Now we look at the next example. Now the function becomes f equal to x squared, and we need to show that f is not a Lipschitz function. This means that we need to show for all c bigger than 0, there exists a x1, x2 such that the absolute of fx1 minus fx2 is bigger than c times the absolute of x1 minus x2. Let's do some sketching first. We know that the absolute of fx1 minus fx2 is equal to the absolute of x1 minus x2 times the absolute of x1 plus x2. So we need x1 plus x2 to be bigger than c. Next, we let c bigger than 0 and choose x1 to be equal to c plus 1 and x2 to be equal to c. Then we can know c times absolute of x1 minus x2 is equal to c. Then we have the absolute of fx1 minus fx2 to be equal to 2c plus 1, which is bigger than c times the absolute of x1 minus x2. Thus, we can conclude that f is not a Lipschitz function. And actually, there is a small truth in example 2. We know f equal to x squared is a continuous function since it's a polynomial. So the converse of the theorem that I said just now is not necessary to be true. A continuous function is not necessary to be a Lipschitz function. This is our last example. Now, the function remains the same, but the domain changed from real number to between -10 and 8. And we need to show that it is a Lipschitz function. We can easily know that the maximum of the absolute of x1 plus x2 is 20 when x1 equal to x2 equal to -10. Therefore, we can let c be 20 and we will prove it easily as shown in the slide. Next, I will talk about some further study on my topic by first introducing the definition of uniform continuity. Let D be a subset of real number. A function f from D to real number is uniform continuous if, for all epsilon bigger than 0, there exists a delta bigger than 0 such that if x1 and x2 are in the domain D and the absolute of x1 minus x2 is smaller than delta, then the absolute of fx1 minus fx2 is smaller than epsilon. Next, the slide shows the mathematical expression of continuity and uniform continuity. We can see the difference between them is the position of x0. This means that when we prove continuity, delta can depend on x0. but cannot depend on x0 when we need to prove uniform continuity. Thus, we will have two theorems related to our topic. The first theorem states that if a function is uniform continuous, then the function is continuous. While the second theorem states that a Lipschitz function is uniformly continuous. Now, I let the proof to you. If you can prove it, you can show your proof under this video. That's all for me. I hope that this video can help you to understand the concept of Lipschitz continuous function. Again, if you like my video, please do not hesitate to like, share, and give a comment under this video. Goodbye and Merry Christmas.